Yesterday, we did the first derivative test. You just didn't even realize we were doing the first derivative test. The first derivative test, yes, and you test it. We did the first derivative test whenever we did the actual table. The end result of our table was our first derivative test. So where f prime of x is greater than 0 or positive, the graph is what? Increasing. And we showed that in our last line of our table, right? The last line of our table, we multiplied all of our positives and negative factors, and then if we got positive, we knew that they were all positive, that it was increasing. So same thing, if f prime of x is less than 0, which means it's negative, the graph is decreasing. And then we also knew that where f prime of x equals 0, we had critical numbers. So those were our max or min, points of inflection. And because we only did polynomials, that's all we had. But if we do radicals or rationals, we might have asymptotes, points of discontinuity, etc. Okay? So the equation that I made you do over there was g of x equals x4 minus 4x cubed minus 8x squared minus 1. And I asked for the critical numbers first. So we have to find g prime of x first, and we get 4x cubed minus 12x squared minus 16x. And then for the critical numbers, we set it equal to 0. And why do we set it equal to 0? That's when m tangent equals 0, and when m tangent equals 0 is when I change from increasing to decreasing, or decreasing to increasing, or increasing to increasing, or decreasing to decreasing. So it's when I get max, mins, or points of inflection, correct? Now we've said if we went from increasing to decreasing, we had a what? Increasing to decreasing, we had a max. If we went from decreasing to increasing, we had a min. And if we went from increasing to increasing or decreasing to decreasing, we had a point of inflection because we only did polynomials, correct? But I did say yesterday that if you had a rational, you might go from increasing to increasing on opposite sides of an absolute value, or no, asymptote. Brain went to grade 11 math. That's the problem. Calculus 30-1 and 20-1 is what I teach throughout the day, so sometimes they all just blend into the wrong words. Right. All right. So what can I take out of this one? 4x. I heard plus x, and I was like, yes, that too. But you said 4. Okay, so we get x squared minus 3x minus 4, which I can factor. I don't even have to decomp. So I get x minus 4, x plus 1. So my critical numbers are x equals 0, 4, and negative 1. Now remember we talked about this. We talked about the fact that you did 30-1 already. And in 30-1 we looked at a whole bunch of graphs, right? So we know what polynomial functions should look like. We should know. We should know what polynomial functions look like. We should know what rational functions, radical functions, all the different functions look like. We should know. Sometimes we have to dig deep into the dark depths of the area of which it's stored, but you should know, okay? So the original of this one is an x4, and it's a positive. We agree? So it's up on the right and up on the left. It's up on the left and up on the right, because it's the same degree and positive, correct? Which means it's going to have an absolute minimum somewhere, correct? Now some people say, well, it can only have one absolute minimum. This one happens too, but sometimes degree 4s make like a perfect W, and they actually have 2 absolute minimums because their minimums are at the same spot. So that's the only way you'd have 2. Okay? So we have our critical numbers. Great. Good talk. So they're either maxes, mins, or points of inflection. And why do I know they're maxes, mins, and points of inflection, but not an asymptote? It's a polynomial function, and polynomial functions are continuous, correct? And continuous graphs don't have asymptotes. That's just how it works. All right. So that was the first thing I asked you to do, was get critical numbers. The second thing I asked you for was intervals of increase, decrease. So the way I always do it is I make myself a number line first. My number line looks like this with my critical numbers. I have negative infinity, positive infinity. Now if they restrict the domain, those won't be negative infinities and positive infinities. They'll be whatever the heck the edge of my domain is, correct? What if a critical number doesn't fit in the restricted domain? You just don't count it because it's not part of the domain they gave you, right? So some people will be like, still critical, and then they use it. But I'm like, no, like your number line should kick that out. So if you always do the number line and you put your critical numbers on it, and this was like a -3, or we'll say it was 0, then -1 you're drawing off the number line, you wouldn't keep it, right, if it doesn't hit the number. So this one is going to be -1 open dot. Why are these open dots? 0s is not drawn to scale. 4. Why is it open dot? Because it's not increasing or decreasing on those values, correct? The interval between them is where it's increasing and decreasing. At those values, it's a max or a min or a point of inflection or an asymptote, not in this case, because your horizontal asymptote is horizontal tangent is at 0. Yep, it's great. I'm doing rationals right now in 30-1. So, intervals of increase, decrease. We set up our table. Put our factors along the top. So I have 4. You could put 4 and x together. I'm not going to, but you can do that. X minus 4, x plus 1, f prime of x. And my intervals are -infinity to -1, round brackets, so they look like coordinates. And then -1 to 0, 0 to 4, and then 4 to infinity. Drawn so well. Don't be jealous. Okay. So when we plug in a value that's between -infinity and -1, I'll pick -2. That's still, I'm just going to do this. Okay, so when I plug -2 in for x, I get negative. -2 in for x on this one, -2 minus 4, negative. -2 plus 1, negative. What's a positive times a negative times a negative times a negative? That's a negative. 3 negatives make a negative.
A negative is a positive times another negative is a negative.
Yeah. So whenever you have odd negatives, you always have negative. Okay, so then between -1 and 0, I have -0.5. So -0.5, negative. -0.5 minus 4, negative. -0.5 plus 1, positive, and this is going to get me a positive. Positive times negative, negative, negative. Ooh, positive times negative times positive is positive. 0 to 4, I'm going to pick 1. So when I plug a 1 in, I get positive. 1 minus 4, negative. 1 plus 1, positive. So I'm going to get negative. Whenever I have an odd number of negative signs, I end up with negative, correct? And then 4 to infinity is 5. So I'll go 5, positive. 5 minus 4, positive. 5 plus 1, positive, positive. So I know, and sometimes it's easier and more helpful to you if you actually sketch the little things beside. So these ones are joined, correct? These two? So I'm going decreasing to increasing. So what should I be getting here? At the joining value between these? A minimum. And what's the joining value? -1. That's the one they share. I don't know what the y is. Okay, then this next one, I'm doing an increasing to a decreasing. So I should be getting a max. And what value do these two share? 0. 0 and 0, right? Then the next one I have decreasing to increasing. So this should be a minimum. What value do they share? 4. So I can't imagine B and C at the same time. Do I have to show mins and maxes if all they ask me for is intervals of increase, decrease? No, don't waste your time. Move on to the next question. Sometimes they'll ask you for max mins. Sometimes they'll ask you for increasing, decreasing. You just need to know how much work you need to do. Okay, so I have not answered the question. So intervals of increase, decrease. Rock in my throat, excuse me. Increase at -1 to 0 or 4 to infinity. Why? Because my first derivative is positive, positive, right? Which was the first derivative test. And then it decreases at -infinity to -1 or 0 to 4. How do I get my max and min values? So because I currently just know where they exist. Yes. So I'm going to go off to the side here. And I'm going to go f of negative 1. I'm not going to do f prime of negative 1. I'm going to do f of negative 1. Correct? Which I don't remember what. X to the 4 minus 4x cubed. Oops. Okay, you're going to tell me. It's, let's see, f of x equals x to the 4 minus 4x cubed. What was the original?
Minus 8x squared minus 1.
So we're going to get negative 1 to the 4 minus 4 times negative 1 cubed minus 8 times negative 1 squared minus 1. So I get 1 plus 4 minus 8 minus 1, which is negative 4. I have two mins. I don't know which one's an absolute yet. Whichever one is the lower y value is the absolute. Okay? Some people are like, I can never tell. Yeah.
And then I thought about it.
Yeah. You got it. Okay, f of 0 equals 0 to the 4 minus 4 times 0. F of 0 is just the y-intercept. And we were taught that if it's in standard form, which it is, the y-intercept is just your constant, which it is, because all the rest cancel. We're going to get negative 1. And then f of 4 equals 4 to the 4 minus 4 times 4 cubed minus 8 times 4 squared minus 1. What is it? 129?
Yeah, negative 1.
Okay. So that one's definitely lower than 9 minus 4. So I think we figured out which one's the lowest. Correct? So we have an absolute min at 4 and negative 129. And then we have local, or sometimes they're called relative. Just depends on what word they use. Min at negative 1 and negative 4. And a local relative max. Why do we know it's a relative max? I don't know if there's things that go higher than it.
Because it's concave up, so it's going to be...
Because we know from 30-1, it's a degree 4. And degree 4s, in this case, arms are up on the left, up on the right with arrows, correct? So they're going to positive infinity for life. So yes, even though this is a maximum, we know it's doing a max, but it's coming back down, and it can't be the highest because there's still arms going to infinity, right? So we have to use the knowledge we have to make educated decisions if it's relative or absolute. Okay, we're going to look at concavity. We'll look at the second derivative test tomorrow because I want you to be able to do concavity the normal way, and then they have this second derivative test, which is not the same like the first. We'll deal with it tomorrow. I want you to learn this properly. So we're going to do concavity on this same question. So concavity uses the second derivative. So if they ever ask if it's concave up or concave down, or the intervals of concavity, nope. Okay. If they ask for the intervals of concavity or whatever, I just find the first derivative because I need it, and then I bypass everything that I just did because I don't need to do it, find the second derivative and go there. Okay? You only need to do what they ask, right? So, what do we have to do? We have to first find our second derivative. Because what we're going to find out is when f double prime of x equals 0, that's where concavity changes. And where concavity changes is where we have points of inflection. Which will make more sense when you go to sketch the graph. So f of x was x4 minus 4x cubed. I forgot it was on that board over there. Minus 8x squared minus 1. F prime of x we did already. It was 4x cubed minus 12x squared minus 16x. And then we bypass that. And we do f double prime of x, which is 12x squared minus 24x minus 16. Now we're going to set that equal to 0. And what can I take out? A 4. So I'm left with 3x squared minus 6x minus 4. What do I have to do with that? I need to factor it. Can we factor it? No. So what are we going to have to do to solve it? Quadratic formula.
I was hoping for
Oh, quadratic formula. So we have 3x squared minus 6x minus 4 equals 0. This is our A. This is our B. This is our C. X equals negative B. So 6 plus or minus negative 6 squared minus 4 times 3 times negative 4 all over 2 times 3. So x equals 6 plus or minus 36 plus 48 is 86. 48, isn't it? Not 86, 84. Can I reduce 84? I know you take a 4 out, you get 21. That's it. Well, let's reduce 84. Take out a 4, that's 21. 4 comes out and it's a 2. So you get 2. There you go. Now this is the triangle. If we can take it out of the triangle, we can. If we can't take it out of the triangle, we can't. We can take it out of the triangle. Bless you. We're going to take out a 2. We're going to get a 3, a 1, and a 3. So x equals 3 plus or minus root 21 over 3. That's a critical number. We don't turn it to a decimal. So on our little chart, we literally have this. 3 minus root 21 over 3. 3 plus root 21 over 3. And infinity. What is that as a decimal? Because remember, we have to pick values around it. Negative 0.5-ish. And 2.5-ish. So we could technically pick negative 1, 0, and 3, let's say, once we do tests for our table. So we still set up the table the exact same. We're going to get a 4. The only problem is we actually have not something nice, right? So our factor is just that. 3x squared minus 6x minus 4. And then we have f double prime of x. And our intervals are going to be from negative infinity to that lovely thing.
And they would normally make you like, use this rule. Would they give you such an ugly thing?
They can if they give you a calculator. In the non-calculator sections, they would give you nicer numbers.
No, but like, what would you give us? Like, would you give us like,
I can give you whatever because you have a calculator.
Yeah, they're just ugly.
They're just math, is what they are. Remember, everyone wants calculators, but the moment you're allowed a calculator, I'm allowed to give you whatever the heck I want for math. So, a lot of people are like, I need a calculator. And I was like, once you get a calculator, you can get anything, bad, good, or otherwise. When you don't have a calculator, I have to give you nice numbers. So. Sometimes a calculator is a curse, not a blessing. Okay, so we're going to plug negative 1 into here. This is going to be positive. Negative 1 into here, I'm going to get 3 plus 6 minus 4. It's a positive, correct? So I get a positive. Then The one that falls between here is 0. So I'm going to get a positive. I'm going to get 0 minus 4, so it's negative. And then I'm going to plug in 3. 3 times 9 is 27, minus 3 times 6, which is 18, minus 4. 18 minus 4 is 22, so that'll be positive. So the second derivative, this is not the second, I don't know why they call the first derivative test and second derivative test. That doesn't follow the same rules, but whatever. Wherever this ends up being positive, we're going to get, do you think concave up or concave down? Concave up, just like it was increasing. It's just straightforward what you think it would be. It's not trickery. And then minus is concave down. The second derivative test says that if you plug these values into the first derivative and they're positive, it's actually concave down. And the second derivative, like, so you actually, it's backwards. Like, if you can use the first derivative to find concavity instead of the second. But we're not dealing with that until tomorrow because it confuses people. So we're going to get this right. So we have concave up, concave down. Please don't use short form on a test. I'm just doing that because I haven't written out the stuff. So my intervals of concavity, I'm concave up from negative infinity to 3 minus root 21 over 3, or 3 plus root 21 over 3 to infinity. And I'm concave down minus. And what's happening when these are changing? Points of inflection is actually what you have. So you have points of inflection at this and the negative of that, the positive and the negative of that, right? Can you type it into your calculator, the original graph? Make sure it's in your calculator, the original. I'm going to type it into mine once people stop grading. So everyone type the original into the calculator because we're going to make all of this make sense and make us feel better about ourselves. Okay. So we should have x to the 4 minus 4x cubed minus 8x squared minus 1, 6. Now I know that my minimum is going to have to be below what? Negative 129 because we found it already, correct? So I'm going to go to my window. You would. Rebel without a cause over here. Okay, so we said that it was decreasing to -1, and then it was decreasing 0 to 4, was it, or something like that? I can't see my chart. But I can see that it's doing that. So this graph, I'm going to give it a little more up top. Okay, so I see that it's decreasing from here to here. Oops. And then it's decreasing from here to here. And then it's increasing a tiny amount from here to here. And then here to here. We agree? Those are increasing. So did that make us feel better about our increase, decrease? Yes. We also know that there is a minimum. We can check them, right? We do second trace min. And we do left bound, enter, right bound, enter, enter. And I get -1 and -4. So I can walk away being like, yes, I did good, right? I done well, right? Now, to check concavity, we want to see, we can put our intervals, we can put in our points of inflection from the second derivative, which are kind of nasty. That's okay. So we're going to go second trace value, and it is going to be bracket, what was it, 3 minus root 21, bracket, divided by 3. Like I have to type it in brackets because I have to type it in all at once, right, for my x? And then it's going to give me the little dot. Do you see that little dot's blinking? Yes. It's blinking right there, David. There it is. Okay? That should be where my concavity is changing. Now, you guys have an addiction to concave up being the whole thing. So you guys are like, concave up, we were taught in 20-1. Concave down, it's the whole thing. Must be, not stop. Has to be equal both sides. Like that's where you're at, okay? But this can be concave up, and then this is concave down on a degree 3, we agree? So where does the concave up and concave, I want concave up, no. I want concave down, no. Oh crap, we've overlapped. That'd be a problem, right? So we can't have a full concave up and a full concave down when they're sharing stuff. So what happens is, we have a concave up, it stops halfway, boom, aka point of inflection. And then we have a concave down, it goes halfway. And do you see this little sharing dot in the middle? That's going to be our critical number of our second derivative. It's where the concavity changes. It's that shared dot. Do you see it? So I know you guys want a full concave up, and I know you want a full concave down, and I know you do because I've taught this long enough, and people will continue to draw them full. And then they're like, I don't know where I have to stop. If you're covering over on both of them, there's a problem. The middle piece where they overlap is going to be your point of inflection. Okay? So this one's blinking, and it's kind of hard to see because it's substantially smaller, but this to here, to that blinker, is what? What does that look like? Part of a what? A concave up graph, correct? And how do I know? Because if I could actually extend it, it would make a whole concave up parabola, doesn't it? So I said from negative infinity to there, it was concave up. Look at me proving myself all right. Okay, cool. Let's go back. Now, the blinker is here. I've just covered it. And then it goes like this. And then I'm concave down, and I just keep going, right? Do I keep going? No, because what's going to happen? It's going to share a concave up. So where do we suspect there's probably a point of inflection again? I erased you. There we go. Halfway down, right? We think that the blinker is going to be somewhere in this region. So it's concave down to here, and then what happens again? It's concave up, which is what we stated. Let's see if I can get the blinker in the right spot. So I'm going to go second trace value, and now I'm going to go 3 plus, oops, in brackets. That's my numerator in brackets because it's more than one term, and a plus sign. Square root 21 divided by 3. Wow, I can't see the blinker. Why can't I see the blinker? Let's see. Where are you? That was disappointing. So I'm not giving up my job and becoming a magician because that didn't work. 3. Work with me. 3 plus root 21 close bracket divided by 3. No, friggin' terrible. Why when I erased it not appear?
It's good first try.
We didn't say acronym.
You didn't say algebra.
Yeah.
So like.
Or luminous, or luminosio, or luminosity.
Yeah, you didn't say anything.
It was like literally, it was there.
Don't worry, someone will edit your video so that you cut the two quick.
I just literally, it was like a build-up. I was like, look, and then there's nothing. All week I've been waiting for this moment.
It's okay, just go into your video class and take like 30 seconds.
Fine. Whatever. I don't need it to work.
Probably not.
I'll edit the file.
Okay. What ruins people's lives is realizing that I can ask you questions that aren't polynomials. That is what ruins your life. So let's start not ruining your life. Start doing some of those. Okay. No. Okay. So guys, the only difference once that we start doing stuff that's not polynomials is our critical numbers can now be asymptotes, the points of discontinuity or not exist. Are you ripping out? Paper up there somewhere?
You told me that before I did.
I didn't know. All of a sudden I heard ripping. And then I was like, oh goodness, they're ripping stuff. This is bad. And then I was like, oh my goodness. I'm just trying to just because that didn't work. I'm trying to put some stuff on you. All right.
When in doubt, point it.
Yes. The land video staff and check. Okay. That's just a joke. Just a joke.
No, it's not.
It was totally a joke. Guys, come on. Man. Okay, we're going to start with this one first. I was going to start with another one, but you'll not be happy with me. So here's example dos. We are going to do everything for this graph. So we are going to go through, we're going to do critical numbers of first derivative, which gets us the increase, decrease, which gets us the max, min, points of inflection, possibly asymptotes. Cool. Yes, because we're not doing a polynomial graph. Dose, concavity, second derivative, boom, points of inflection, drop the mic, done everything. That's what we're going to do. What's great about this is you have pre-knowledge that you keep forgetting you have. So when I give you this rational graph, you're going to know what the asymptotes are already because you know them, because you have a method to figure them out before we get there. So then when we get a critical number that lands on them, you're like, boom, they're asymptotes. I know this already because I'm a genius. Okay? Don't forget you have knowledge before this class. Like you were blessed with something. Okay? Don't forget about it. So we have y equals x squared over 1 minus x squared. So I got myself here a rational. Rationals have some asymptotes. Yeah? Cool. Okay. Let's just use our 30-1 knowledge. This isn't a 20. This isn't an AP question. This isn't -1. I don't write anything. I literally just wrote an equation. There's nothing written here, guys. We're in -1. Okay? Zoom. We're back. No, I just made you go back in time. This is how good I am. Boom. November. No. Boom. December. We were doing some. I think we did this in September, but whatever. Anyway, somewhere in time. Boom. We're back. We have a rational function. So what we always do is we factor. If stuff cancels off, we have a what? Point of discontinuity, which we call a removable discontinuity now, or jump asymptote if it just anyways, good times. We have those. So we're going to factor first. We agree? Okay, so we're zooming back to grade 10, and we're going to factor. Zoom, and we're here. We're not at home anymore. In grade 10, you got sent home. In grade 10, you would have just gotten sent home.
Can we go back to grade 10?
Because my daughters had their leprechaun traps at school, and they never got to see them ever again. I believe I got sent home with them. It was the weekend of the leprechaun traps.
What is a leprechaun trap?
You trap a leprechaun. I thought it was very, like, isn't the wording of that?
Yeah, well, I didn't know like there was cheese and something.
There was no cheese. This is not a mouse trap. This is a leprechaun trap.
I'm sorry, if you put cheese in the box.
Mine got Lucky Charms because they're magically delicious. All right.
It'd be interesting. 3 flies.
Okay. If we factor the bottom, what do we get? 1 minus x and? Yeah, and I put the plus first because my brain went that way, so I'm going that way. It doesn't matter. Now, does anything cancel off? No, and 30-1 self would say, oh, there's no point to discontinuity. But we know that if there's stuff on the bottom, those lead me to what? What kind of asymptote? Vertical asymptote. See, there's brain matter. You guys still have stuff there. You remember. Good job. You guys always sigh when I bring up 30-1 and say you remember nothing. Boom.
3 people answer. The rest of us are hopeless.
The rest are keeping it inside. Okay. Vertical asymptote. At x equals what? -1 and +1. I don't know why I wrote it above the, but whatever. I'm a rebel.
That's all.
I'm a rebel without a cause.
That's all.
There is a button that you can pick that button when you go to use equation editor in Word. Just so you know. Fun fact. I didn't mean to do it that way, but I'm not changing it. Okay. So we have x equals a negative and +1, correct? And that's where our asymptotes are going to be. So I know right off the hop, because I'm a genius, so are you, those are going to be critical numbers in my first derivative. because your intervals of increase and decrease change on opposite sides of your asymptote. Now they might go increase to increase, they might go decrease to decrease, but something's happening on either sides of those. So I know that when I go to the first derivative, I better get those two. Okay? Now, I will also get other critical numbers if there's actually maxes and mins in this. But most often in rational functions, you have just like zoom and a zoom, right? And you don't actually have asymptote or a max and a min. Sometimes though you do. Sometimes you'll have like an asymptote, and then you have like a curve here, a curve here, and then like a that in the middle, which would get you a max. Sometimes you have an asymptote. You have a this and a this and a this. So you have a point of inflection. So there are other critical numbers that could pop up if this graph actually had a max or a point of inflection in it. Okay? But I know for a fact those two have to be there. Now I also know there's going to be a horizontal asymptote, which doesn't appear anywhere else, but let's just use our brain knowledge and remember what it is. So a horizontal asymptote is a y-equal asymptote, so it's not going to happen in my critical numbers because my critical numbers are x's, correct? But I'm going to talk about it anyways. Horizontal asymptote. The degree of the numerator is the same as the degree of the denominator. They both just happen to be x squared. What do I do? Coefficient of the same degree. Exactly. So this one's a 1, this one's a -1, so it's going to be y equals -1. And that's helpful if they ask us to sketch. We're also going to talk about limits as we approach infinity. And limits as we approach infinity and negative infinity are actually going to get us our asymptote. And the reason why that happens. Okay. So, never happened. It wasn't my friend. Okay. So you're going to find y prime. Go. Super fun. Quotient rule. Now, are we going to use it with this thing and then do product rule embedded in a quotient?
No.
Stop
Yes.
the madness. Don't
It's
go.
fine.
Revert back. Use this one. This is your F and this is your G. Try it out wherever you are. So here's F. Here's G. G is 1 minus x squared times F prime, which is 2x, minus F, or G prime, doesn't matter, which is x squared, times G prime, which is -2x, all over G squared, which is, these are nice because it literally just gets squared and you're done. You don't put those together, you don't FOIL it, you don't do anything to that denominator. Now, was there a chain rule embedded in either of these? No. When there's not a chain rule embedded, you will distribute. That will be your next step. Okay? So if there's a chain rule embedded, your next step will be take out a GCF. If there's not a chain rule embedded, your next step is to distribute, collect like terms. Those are the two differences. So we're going to distribute. Boom, boom, boom. If there was chain rule, I would GCF, but because there's no chain rule embedded in the F and the G prime, boom, boom, distribute. Y prime equals 2x minus 2x cubed plus 2x cubed over 1 minus x squared squared. Got it. Excessive amount of squares. So these cancel, and I'm left with y prime equals 2x over 1 minus x squared squared. So my critical numbers are still going to come from the 1 minus x squared squared, right? And from the 2x. What critical numbers will I get from this one? The same ones as before, because you just take your denominator, set it equal to 0, right? So if I go 1 minus x squared equals 0, I would square root, plus or minus, but it'd still be 0. And we did this above, 1 plus x, 1 minus x. X equals plus or minus 1. I won't write it ugly this time. So that's my critical number, but I also have, and I knew those were going to come. I knew I was going to have those. The fact that I have those makes me happy, because that means I actually did something correct, because I knew I needed to get them. Correct? Okay. I also have another thing, though. I have this 2x on the top. So my critical numbers are x equals 0 and plus or minus 1. We agree? Now, the reason why we made the chart the way we did is because if I take all my factors, I have a factor times a factor times a factor times a factor. And if I just figure out what the signs of each of those factors are, I can figure out the sign when I multiply them all together, correct? So this one is, we have something on top, something on bottom, correct? If I find the sign of when I fill into the top and I find the sign of when I fill into the bottom and I divide them, I'll get the sign, right? We agree? Sign, sign, get the sign. We agree? So I could do it all, instead of doing a chart, I could just plug it into that whole fraction. Just like I could have plugged it into the first derivative and gotten an answer, correct? But it's harder when you don't have a calculator to do the bigger numbers and then multiply the big numbers together and get a big number. So, what are we going to make our chart out of when it's a division? It's still just going to be, we could go 2x together, we could go 2, we could go x, it doesn't really matter, right? So we could say 2x, and then we can say the denominator, which is 1 minus x squared squared. Now the reason why I like this denominator is when you square anything, what's going to happen? So I'm going to get plus, 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 plus the whole way down. No matter what I plug in there, it's going to turn positive. That's why I like when my denominator squared. I'm like, thank you. Don't really care what the numbers are. You always turn positive. This actually makes me happy. A lot of people see this and they're like, oh, it's going to be hard. No, it's not. They're going to be all positives. This is going to be really easy as well. Whatever it is what it's going to be. So this is actually an easier chart than the previous polynomial one. So we still have to get our number line to get our intervals. So our number line is going to be negative infinity, negative 1, 0, 1, infinity. So I have negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to infinity. So, like I said, no matter what I plug in here, if I plug in a negative 2, negative 0.5, a 0.5, or a 2, when I square any of this, whatever this results in, I'm going to get a positive, 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 and a positive. Because when I square a negative, I get a positive. When I square a positive, I get a positive, right? Now these ones I'm going to plug in negative 2. 2 times negative 2, negative. This one I'm going to plug in negative 0.5. 2 times negative 0.5, negative. I'm going to plug in 0.5. 2 times 0.5, positive. And then here I'm going to plug in a 2, positive. So what's a negative divided by a positive? Negative. And then a negative divided by a positive is a negative. Positive divided by a positive. Positive. Positive divided by positive. Positive. Now, when it was a polynomial, I went positive, so increase to decrease got me a max, decrease to increase got me a min, correct? Because every single one of them was a point of inflection or a max or a min. We agreed because it was a polynomial. So what I'm going to do to help myself out here is I'm going to figure out where the asymptotes are so I don't like start drawing maxes and mins, okay? So I know at positive 1 and negative 1 I have 2 vertical asymptotes. I knew that right from the beginning because I had that knowledge. So the negative 1 is being shared here, correct? So there is a vertical asymptote here. And what's it doing on both sides of this asymptote? Decreasing, then decreasing. So what does that look like? It's probably going like this. It's probably curving. Decreasing, and then decreasing. Right? That's what we think it's probably doing on both sides of that. Okay. Where's my other asymptote? I have a vertical asymptote here at the shared 1. Looks like a beta or an alpha, I mean, but it's not, it's an X. So what the heck's happening in that middle piece? Yeah, it's decreasing, then it's increasing. So what am I guessing there might be there? Decreasing to increasing, minimum. Point of inflection is when I get decrease to decrease or increase to increase, correct? So I'm decreasing to increasing, so I'm guessing that there's a minimum. And what are they sharing? 0 and some. That's my guess. Educated. Yes. So type it into your calculator. Let's see if our educated guess is right. This is where you type it in and you're like, oh, if you type it in wrong, it really sucks. Because then you just think you're wrong, but you really just can't type it into your calculator. So please don't be that person. So type it in, numerator in brackets, denominator in brackets, or use alpha y equals enter. Correct? So everyone's typing it in, and then we feel better about ourselves or bad. That's where we're at this point. Sorry? You have them on your normal test, yeah. Oh, putting marker. Sometimes I ought to. Okay, so what did we get? Alpha y equals enter. What was the top? I don't remember.
No way, that's not it.
You still my heart. We did well. Okay, let's go. So we said that it decreased on the left of 1, correct? Boom. What? And then we said it decreased on the right of -1. And then at 0 was a critical number, and then it did what? Oh, it increased on the, and then it, genius level, that's where we're at. We know we got it right. Yeah, cheer. Okay, now we could just go second trace value 0, and we know we have a minimum at 0, 0. How could we do it algebraically? Wow, this is, put it back into the 0. In fact, so we get 0 squared over 1 plus 0 squared, which 1 minus, and that got me 0 nonetheless. So if I want for intervals to increase, decrease, we increase from where to where? 0 to 1, 1, or 1 to infinity. Can I say 0 to infinity? No, there's always 1 or 2 of you on the test who give me 0 to infinity. I'm like, girl, please. I literally said do not do that. Okay, you cannot go from 0 to infinity because at 1 it is not increasing. At 1 it has a horizontal asymptote. At 1 it has a horizontal line, a tangent slope at 1, right? It's at 0, not increasing. It ain't positive. Okay? Yeah.
Why do you always use like the round brackets?
Because you can't equal those values either. At those values, your tangent slope is 0. Your tangent slope's not positive. So if we want where it increases, it's where the tangent slope is positive. So if you put square brackets on the 1 or the 0, you would say that it's actually increasing there when it's not. It has a tangent slope of 0. And then decrease from negative infinity to -1 or -1 to 0. It has a minimum. It's a rational. Will a rational ever have an absolute minimum or an absolute maximum?
No.
No, because its arrows are going up somewhere to life and down somewhere to life, which is called positive and negative
I
infinity.
don't think we got it.
No,
I agree.
yeah. Okay. Now, what else can I ask you to give me?
Concavity.
Yes, concavity. So y double prime, go. Okay, so we're going to get G times F prime minus F times G prime. G prime is going to be 2 bracket 1 minus x squared to the 1 times negative 2x, which gets me negative 4x 1 minus x squared, which means I'm using chain rule. And then I'm going to get 1 minus x squared squared squared. Well, the squared and the squared, these two can join and become a 4. They just can't go into here.
Yeah.
So the catch here is that I used a chain rule on my G, correct? So if I don't use a chain rule on F and G, then I will distribute collect like terms. If I use a chain rule in F or G, the next step is to always GCF that out. There's 2 different steps. If the chain rule exists, you GCF. If the chain rule doesn't exist, you distribute collect like terms. People are like, I don't know what to do. Those are the 2 things. That's it. There's no other like options. Okay? So y double prime, we're going to take out a 1 minus x squared. And then we're going to be left with 1 minus x squared times 2. And then this is going to cancel off, so I'm going to get plus 8x squared. Yeah, you can take a 2 out.
Okay, you can take it out?
Yeah.
Yeah, I was gonna say, you should.
And then we're going to get 1 minus x squared to the 4. Y double prime is going to be 2 bracket 1 minus x squared. And then this we're going to get 4x squared. Well, this will be 1 minus x squared plus 4x squared. So when you collect like terms, you're going to get 3x squared plus what? There's no 2. Oh. And then you get 1 minus x squared to the 4. So I'm going to get critical numbers at...
Did you just summate it up to these cube roots or cube?
Yeah, it doesn't really matter.
What happens to the inside? Would you just collect like that?
Yeah. I have this on the inside.
Okay.
So we have y double prime equals 2 bracket 3x squared plus 1 over 1 minus x squared to the 3. So this here is going to get me critical numbers of plus minus 1. That hasn't changed. The top is an addition of squares. Does an addition of squares ever get me answers? No, because what are you going to do? You're going to subtract the 1, you're going to divide by 3, and then you're going to take the square root of negative a third. Can you take the square root of a negative? No. So whenever you have an addition of squares, you can't get a critical number. If you're like, I will never remember that, you're going to take your factor off to the side, and you're going to say 3x squared plus 1 equals 0, and you're going to solve it just like you did the bottom one. You get 3x squared equals negative 1. Divide by 3. X squared equals negative a third. Root it. When you root it, this is not possible. So no critical numbers from this one. So the only critical numbers we have are just the asymptotes. And our concavity is going to change on opposite sides of the asymptotes, which makes sense because, go back to our graph, this is concave down on the left of the asymptote. This is concave up between the asymptotes, and then this is going to be concave down, technically, on the other side. Because it curves in the downwards fashion. If it was concave up, it would be going like this.
Oh, it'd be on the top.
Yeah. So, we go to make ourselves our little chart. And we're going to have a 2, and we're going to have a 3x squared plus 1, and we're going to have the denominator, which I would have liked to have left because now it's a cubed and it makes a problem. Why does a cubed make it harder?
Because if it's negative,
Because you actually have to find out what's inside that bracket. Now we have from negative 1, negative infinity, negative 1, 1, infinity. Yes, thank you. So we're going to have negative infinity to negative 1, negative 1 to 1, 1 to infinity. Leave it. These are all going to be positive, because 2 doesn't change.
oh, I see.
Now, This is a squared. Do you see that? No matter what I plug into a squared, what's going to happen? Positive times a positive is going to be a positive plus 1 is going to be a. So no matter what I plug into this one, they're all going to be positive. So it's all just completely dependent on the denominator. You guys should be paying attention or you will be lost, misters. I'm on my phones today. Okay. Well, that's because you're on your phone way more than normal. So if I plug in negative 1.5 and I square it, am I going to get a larger number than 1? Yeah. So this is going to become negative. Then if I plug in a 0, 0 squared, 1 minus 0, positive cubed is positive. And then if I plug in 1.5, the 1.5 gets squared, but there's a negative sign in front. The negative doesn't join this. The negative sits here. You're literally putting the 1.5 into here. 1.5 squared is a bigger number. 1 minus a bigger number is a negative. So I'm going to get a negative, a positive, a negative. And what did I say? I said this was concave down. I said this was concave up, and this was concave down on my graph. So it makes me feel better. And I told you where the concavity changes is a point of inflection or an asymptote. And in this case, these are asymptotes. Are there any points of inflection on this graph? No. So this is concave down from negative infinity to negative 1 or 1 to infinity. And then it's concave up from negative 1 to 1.